All right, let's jump right in. Welcome to this explainer on Chapter 15 of Space Mission Engineering, the new SMAT. Today, we're going to completely demystify the absolute core of space mission design, the payload. You know, if you've ever looked up at the night sky and wondered exactly how a satellite actually does its job, whether that's hunting for the edge of the universe or just beaming a Wi-Fi signal to your phone, you are in the exact right place. We're going to break down the mission builder's blueprint step by step. So here's our roadmap for today. First, what is a space payload? Second, the subject, active versus passive. Third, seeing the electromagnetic spectrum. Fourth, the 10-step design process. And fifth, real-world payload examples. Let's explore how engineers build a space mission piece by piece. Starting with part 1, what is a space payload? We are starting right at the heart of the spacecraft. Basically, this is the entire reason a space mission even exists. The textbook definition tells us that a payload is the total complement of equipment carried by a spacecraft that interacts with the subject in performance of a particular mission. So the crucial point here is that a satellite isn't just some shiny silver box floating in the sky, right? It's a meticulously designed tool. Everything else up there, the solar panels, the thrusters, the communications dishes, is literally just there to support this one crucial element, whether that's a camera taking a picture or a sensor measuring a magnetic field. And these payloads come in a really wild variety of flavors. You've got observation tools like the Hubble telescope, or communications payloads handling your DirecTV and GPS. Then there are in situ payloads. These are the ones that actually touch the environment they're studying, like the Mars rovers. There's even a category called action at a distance for things like space-based power transmission. And of course, human spaceflight payloads, where the human crew itself and the life support keeping them alive are the central focus. Moving to part 2. The subject, active versus passive. Once we know what our payload is, we have to tackle the core tension of the engineering process. How does this hardware actually interact with the universe? Engineers have to ask a fundamental question right out of the gate. What is the system measuring or working with? This is absolutely crucial because this subject dramatically dictates the performance, the cost, and literally the entire design of the mission. If your mission is to track forest fires, your subject might be the heat of the fire, the smoke, or atmospheric changes. Choosing which one to focus on changes everything. This brings us to a massive fork in the road. Is our subject active or passive? An active subject is something we can actually control or modify, like a GPS receiver in your car. Because we control it, we can shift the complexity. We can make the satellite super powerful so the receiver on the ground can be cheap and simple. But a passive subject, like a distant quasar or a raging forest fire, it doesn't care at all about our engineering constraints. Its characteristics are totally fixed, and our payload simply has to be good enough to observe it exactly as it is. Think of it kind of like a flashlight. A passive payload just sits there and watches what the universe provides, like a standard camera. But an active payload, like a space-based radar, is essentially taking a flash photograph in the dark. It brings its own illumination. This is an absolute game changer because it lets a satellite penetrate heavy clouds or look through light foliage. But it requires massive amounts of power and generates intense heat, making it a massive headache for the thermal engineering team. All right, part 3, seeing the electromagnetic spectrum. To really understand how payloads see, we need to talk about their ultimate toolkit. Almost all space payloads operate through the electromagnetic spectrum, and the scale here is just staggering. We are talking about spanning at least 16 orders of magnitude, from ultra-short exahertz gamma rays all the way down to kilohertz radio waves that can be kilometers long. Your payload design entirely depends on which exact slice of the spectrum you're targeting. A comm satellite relies on radio frequencies to punch through the Earth's atmosphere, whereas an Earth observation satellite is going to lean heavily on the visible or infrared bands. And you have to design for absolute extremes across that spectrum. For example, if you're building an optical sensor relying on sunlight, you are designing for the sun's blistering 6,000 Kelvin brightness temperature, meaning you better shield your instruments from melting. But on the flip side, if you're measuring the cosmic background radiation, you're hunting for a whisper of a signal at a freezing 2.7 Kelvin. You have to capture these faint signals while filtering out all the stray noise scattered by the Earth's atmosphere. Let's bring this all together in section 4. The 10-step design process. We've talked about the physics, but how does the engineering actually happen? It happens through a rigorous 10-step methodology. Step 1, select payload objectives. 2, conduct subject trades. 3, develop an ops concept. 4, determine required capability. And 5, identify candidate payloads. Basically, these first 5 steps take us from a completely blank piece of paper to figuring out exactly what our payload must output and what hardware might actually be able to do the job. Let's ground this in a hypothetical example, the FireSat-2 mission for tracking wildfires. We don't just say, hey, let's go find fires. By step 2, we defined our exact subject trait. We need to distinguish a 3-degree to 10-degree Kelvin temperature difference against the normal background of the Earth. By step 4, that translates into a hard requirement for 12-bit radiometric capability. Put simply, the sensor has to be sensitive enough to detect thousands of tiny distinct shades of heat. That math then points us to a couple of candidate sensors in step 5. Then we hit the second half of the process. Step 6, estimate candidate characteristics. 7, evaluate and select a baseline. 8, assess life cycle cost. 9, define derived requirements. And 10, document and iterate. This is where the really hard choices happen. Engineers have to match their dream performance against the brutal realities of cost, mass, and power constraints. Back to FireSat-2. This perfectly illustrates the classic cost versus performance trade-off. Say our first candidate sensor is amazing, but it spits out 10 megabits of data per second. To afford the giant transmitter needed for that, engineers might have to restrict the mission scope so the satellite only looks for flaming fires, not smoldering ones. Then, to save even more money, they might have to completely repackage the payload so it can hitch a ride on a less expensive Ariane rocket. It's a dance, right? The payload dictates the mission, but the budget dictates the payload. And finally, part 5, real-world payload examples. Let's look at how this rigid 10-step process creates some incredible, vastly different real-world missions. Even though the methodology is identical, the outputs vary wildly. On one extreme, you have the multi-billion-dollar Hubble Space Telescope. Its passive subject is the distant universe, so it required a massive 2.4-meter mirror and was uniquely designed to be serviced by astronauts. But on the complete opposite end of the spectrum, you've got QuakeSat. This is a tiny 4.5-kilogram CubeSat that cost about $1 million. It deployed a 70-centimeter boom to measure low-frequency magnetic fields to study earthquakes. Both are brilliant, just sized completely differently based on their objectives. And speaking of active subjects, check out TerreStar-1. Back in 2009, this was the largest commercial communication satellite ever built. Remember our active subject trade-off? Since the subject was millions of users with tiny, low-power handheld mobile phones down here on Earth, TerreStar-1 had to do all the heavy lifting. It literally unfurled an enormous, mind-boggling 18-meter reflector in space just to generate 500 individual spot beams. It kept the ground tech wonderfully simple by making the space tech incredibly complex. So we've seen how payloads are the ultimate tools for interacting with our universe. They're the keys to answering our biggest questions and connecting our world. Taking all of this engineering methodology into account, I will leave you with this provocative thought to ponder. If you were handed a blank check to design a payload to solve any problem on Earth, what exact subject would you measure, and how would you build it? Thanks for joining me for this explainer, and keep looking up.